Okay, so for part 2 of homework 7-2, we'll go ahead and pick up here with question 7. Okay, so we've done the first couple of questions 1 through 6 in part 1, obviously. Okay, so we'll get going then with question 7. This one's, again, just kind of an old review problem. Doesn't hurt. It's been a little while since we've seen it. So a bird drops a walnut that it was carrying in a beak. If the bird is flying horizontally at an altitude of 23.5 meters and the walnut travels a horizontal distance of 12.5, how fast was the bird flying? Well, the important thing is they tell us it was flying horizontally, right? So here's my beautiful bird. It looks more like an airplane, but I'll give it little feet. Right, so there, I know it's a bird. Okay. He's flying horizontally before he drops a walnut, okay, which is important, right? The reason that's important is if the bird is flying horizontally, what does that tell us about the initial vertical velocity? Well, it tells us the initial vertical velocity is 0. So we know the altitude of the bird. We know the altitude is 23.5 meters. We know the distance that the walnut travels before it hits the ground is 12.5 meters. So if I want to find how fast the bird was flying, if I want to find my horizontal velocity here, the important thing is I know the horizontal velocity is constant, and that allows me to use my constant velocity formula, which is simply delta x over t. And so I know my delta x, I know how far it's gone horizontally is 12.5, so then I just need to find my t. Well, I can use vertical kinematics to find t. I know my initial vertical velocity is 0. I know the height, my delta y if you prefer to think of it that way, is 23.5, and then I always know, right, my acceleration is negative 9.8, or in this case, because I'm dropping it, I can go ahead and just define that to be positive 9.8. Okay, but I do know that velocity, I do know that initial height, and I do know the time. Okay, so now it's just a matter of using kinematics. Well, if I jump to delta y equals v sub 0 t plus 1/2 at squared, again, the important piece is my initial velocity is a 0, so 23.5 equals 1/2 my acceleration of 9.8 times t squared, and then just solving for t the rest of the way, I should find t to be about 2.19 seconds, I believe. Okay, so that's what I calculated for this. And then once I have the time, again, all I need to do is bring that together, right, with my horizontal velocity up here with my constant velocity. So I know I went a distance of 12.5 meters horizontally. It took 2.19 seconds before that rock fell from the bird's mouth and hit the ground. So it still took 2.19 seconds to travel that distance horizontally. So I calculate those numbers and I get that to be about 5.71 meters per second. So again, a good chance to review this problem, but hopefully not too bad for most. Question 8 on this homework is actually hopefully pretty straightforward, right? I guess not necessarily straightforward since we're involving torque and it's rotational. I know, I'm hilarious. But anyway, okay, so they tell us a force is applied to the lid, generates a torque. So really the question is, what's the relationship between torque and the force, right? Well, torque we know is force times the radius. They don't give us any type of indication, so we will go ahead and assume that this force is being applied perpendicularly. Probably not the best worded problem for that sense, but we will assume that it's applied perpendicularly, which means it's just 155 Newton times meters would equal my force of 235 newtons, and then times my radius. So solving for the radius, right, relatively easy calculation. Again, don't want to waste your time on that, but I do want to make sure we're comfortable with it. Okay, so solving for the radius, we should get that to be about 0.66 meters. Okay, obviously a big radius for a jar, but maybe we'll assume it's a very large jar. So question 9, an 82 kilogram diver stands at the edge of a light 5.0 meter diving board. Okay, so the fact that the board is light tells me I don't have to worry about the weight of the board, which is nice. It'll reduce one other force out of this, which is supported by 2 vertical pillars that are 1.6 meters apart, as shown in the figure below. Find the magnitude and the direction of the force exerted by each of the pillars. So we're trying to figure out exactly what the forces of these 2 pillars are going to do. Okay, so right now it's a little bit of a question mark, right? We know that the force of gravity on the diver is definitely going to be pulling down. So the force of gravity on the diver, right, would come from his mass of 82 kilograms times 9.8. If we want to go ahead and calculate that number so that we've got it to work with, we could. Okay, but ultimately that's going to come up into play into the calculations. Okay, so the reason I said it's a bit of a question mark is, strictly speaking, we don't know if both of these forces are pushing up. Both of these forces, maybe not both these forces, but maybe one of the forces is pulling down and one of the forces is pushing up, but we don't necessarily know which one, at least not yet. Okay, so if we just try to work with forces, we get a little bit stuck, right? There's too many variables. There's these two unknowns. Okay, so the question becomes, how can we use torque to help us eliminate one of the unknowns? Well, if we put the axis of rotation at either one of these pillars, it would eliminate the force at that pillar from torque, right? Since torque equals force times distance, if we set the axis of rotation at one of those locations, the radius would be 0, and therefore that torque would be eliminated. Okay, so if we want to simplify this problem a little bit, choose either one of those two locations as the torque. Now, it doesn't matter which one. Okay, so if I would like to choose this as my axis of rotation, I absolutely can do that. Okay, so I'll go ahead and work with it at this point. If you do use point B, it's going to be a very similar process. Okay, but I'll start with this point here, and then you can maybe see how it's comparative if you were to choose at point B. Okay, so if I'm starting with point A as my axis of rotation, then there's two forces that are going to generate torque. Okay, there's this unknown force at B, and there's this force over here of gravity that's acting on the diaphragm. Well, if we look at the force of gravity acting on the diaphragm, that force would cause this beam to want to rotate downward, right? It would cause a torque that generates this clockwise direction. We know, though, that the diving board is not actually rotating, and what that tells us is this pillar over here at B has to be doing something that generates a torque that opposes that, right? It cancels out, it negates that torque. Okay, so that tells me that pillar B, the force here coming from pillar B, has to be upward because it has to be generating a torque that's opposite to that. So here's where we have to be careful. The force at pillar B does not necessarily equal the force of gravity, and in fact we'll see that it shouldn't, right? Because the only thing we know for sure is the torque caused by pillar B equals the torque caused by the force due to gravity of the guy. Okay, that's the only thing we know for sure, since the board is not rotating around this point. And since those two beams, since the pillar and the person, have a different radius, we know that in fact the forces can't be equal. So we'll see that here in just a second. Okay, the good news is both of those forces are perpendicular. So the force of the pillar B times the radius that it is from the axis of rotation would need to equal the force of gravity of the guy times the radius that he is, so I'll call it radius of the guy, from the axis of rotation. Again, the biggest thing with the radius is we need to make sure we realize it's the distance from the axis that we chose to rotate it around. Okay, so as I'm solving this problem, as I'm working through it, okay, my force B would need to be equal and opposite, right? My force B would need to be equal and opposite when I take that times the radius B to the other measurements as well. So I can go ahead and plug in those measurements. Sorry about that there. I can go ahead and plug in the measurements. So I don't know what that force is, but I do know that it's 1.6 meters from the axis of rotation. Okay. I do know what the force of gravity of the guy is. It's my 82 times 9.8, and I also know that the diver is the entire 5 meters away. Okay, so if I look through this equation, the only variable I have is that force from that second pillar, from pillar B. Okay, so if I go ahead and solve for this, I should get something to where my force on pillar B is about 2,511. So maybe I'll go ahead and round that off at 2,510 newtons. Okay, so the approximate force at pillar B is somewhere in that ballpark, depending on your exact calculation, maybe round it a little bit, but somewhere in that ballpark. Okay, so here I found one of my forces. And you might be saying, well, do I have to do torque again, right, to find then the force at pillar A? The good news is no, we don't, because now if we just take a step back and we look at our forces, right, so now instead of worrying about torque, if I just look at my forces, I know that force B is pushing up, I know that the force of gravity of the diver is pushing down. If I look at those two measurements, force B is pushing up with 2,510 newtons. The diver's force here is going to be less than that. If we calculate, if we go ahead and calculate 82 times 9.8, which I'll do here real quick, 82 times 9.8, should be about 804 newtons pulling down. So if we look at just those two measurements, this force pulling down is not enough to balance this one out, which means that pillar A actually also has to be pulling down. Okay, so the relationship that then exists between my forces is the force of A plus the force over here of gravity on the diver have to be equal and opposite to my force of pillar B. Since I know they're in equilibrium, I know that the two vertical forces going down have to be equal and opposite to the force going up. Okay, so again, what I'm saying is the force of A plus the force of the diver have to be equal and opposite to my force of B. Well, the good news here is, just looking at these three, I now know two of the measurements. I know my force for pillar B, and again I know the force of the diver based on his mass. Okay, so then just solving for A, depending on what your answer for pillar B was, I should get somewhere in the ballpark, right, of 2510 minus 804, so somewhere around 1706 newtons, or again, if you want to go ahead and round that off, I said 1706, so maybe about 1710 newtons if we're using 3 sig figs. Okay, so finding each of these, hopefully once you get that first one, the second one's not too bad. Had I wanted to choose this as my axis of rotation, I absolutely could have. The force of gravity of the guy would need to be, the torque caused by that force would need to be equal and opposite to the torque caused by force A. Okay, so would have been a slightly different perspective, but ultimately the relationship we still work with would be relating the torques of the two equal. So question 10 is a good question, not necessarily because it's particularly difficult or eye-opening, but just because how often do you get, say, adult nitwits in a question, right? Okay, so a pair of adult nitwits sits balanced on a teeter-totter. One of them, whose mass is 45.2 kilograms, is 1.30 meters from the point of balance. The other chatterhead is 2.15 meters from the point of balance. What is the mass of the second person? Okay, so obviously with a situation like this, they don't give us a diagram, so one of the first things I would recommend is to try to get a feel for what this is saying. Okay, so we don't necessarily know how long the teeter-totter device is, right? But we do know that wherever that point of balance is, wherever they're balanced about, person 1 sits over here, right? He's happy to be on the teeter-totter. He's a distance of 1.3 meters from the point of balance. Okay, so he's sitting over there, and then the second person sits a distance of 2.15, so a little bit further away, right? 2.15 meters from the point of balance, so he's sitting over here. He or she, I guess it doesn't specify, okay, sitting over here somewhere. So once again, very happy to be balanced on the teeter-totter and not moving or bouncing up or down or enjoying themselves, just happy to sit there. Okay, so those two individuals are sitting balanced. We're asked to find the mass of the second individual. Okay, so we're looking for the second person's mass. They give us the mass of the first person. Okay, so again, not a terribly difficult problem, as cheesy as it is, as cheesy as I made it. Okay, it's just a matter of balancing the torque. Okay, so the important thing here is we know that the only two forces acting on this beam would be the force of gravity of the first person pulling down and the force of gravity of the second person pulling down. Okay. So the force of gravity between those two don't necessarily have a direct relationship, but the torque that's generated by those two forces do have a relationship, right? The torque caused by the force of gravity, the first one, would want to cause this beam to rotate in the way that I've drawn it, in the counterclockwise direction. The torque caused by the second person would want to cause it to rotate clockwise. But if they're sitting balanced, if they're not moving, we know that those two torques have to be equal and opposite. Those two torques have to be balanced out. Okay, so again, torque 1 needs to equal torque 2. We know that torque 1 is calculated as force 1 times the radius from the center of rotation. Torque 2 would be force 2 times its distance from the center of rotation. Okay, so then solving for this, we need our force of gravity, so we do want to make sure we're accounting for not just the mass, but also the acceleration due to gravity. So mass times gravity times the radius would equal mass 2 times gravity times the radius 2. Now the good news here is both forces are accounted for through the acceleration due to gravity, so really I actually can cancel the g out. Okay, so if I do that beforehand, it just simplifies this a little bit, but I would get mass 1, so 45.2 times the radius from the center, so times 1.3, would equal mass 2, which is my unknown mass, times again the radius from the center, so 2.15. In solving for that, I would find my second mass to be about 27.3 kilograms. And make sure that makes sense, right? Make sure as you go through this that you can kind of get a feel for that. If the distance, right, if the radius increases, that means we don't need as much mass to produce the same amount of torque, right? The further away we are, so if the radius goes up, then the torque is naturally going to go up as well, even if we don't have as much force. Okay, so 27.3 seems like a pretty reasonable number given those two measurements, and that is in fact where I want to be.